Okay, now the next section in the book in chapter 10 you'd want to read is 10.7 on kinetic molecular theory. Very theoretical. You want to probably follow the PowerPoint, and I'll give you an interactive demo on kinetic molecular theory. I'll put up a video on that. I'm going to talk about 10.8, and now we're getting into molecular effusion and diffusion. And again, I'll put up a video separate on effusion and diffusion if I haven't already. By the time I put this up. Okay, diffusion is how fast is a gas going from a high concentration to a low concentration. And this happens because of kinetic molecular theory. Gases are in constant, rapid, random motion. So they tend to go into more entropy, more disorganization. They go from being highly organized to less organized. And that's the second law of thermodynamics. Effusion is when that gas passes through a small hole. You might see effusion if you have a regular balloon that you've blown up. You might notice that over the course of a week, if you have a latex balloon, the balloon will go from larger to smaller. And what's happening is the individual molecules are getting through small pore openings in the balloon. And the smaller that molecule is, then the faster it's moving, because the mass is related to the velocity of the particle. Okay, and so the lighter the particle is, the faster it's going to be moving. The heavier the particle is, the slower it's going to be moving. So you might notice that if you have a balloon full of helium, that balloon's going to shrink much faster than if you had blown it up full of air. Because the air is heavier, the air is going to be moving slower and it'll be diffusing out of the balloon faster. If you have a real light gas like hydrogen or helium in it, then it's going to fuse out faster. And you might notice that if you have them, the mylar balloons, the metallic balloons, they last a lot longer, and the reason is they have less porosity. You're not going to have too many pores in it, so the balloon, the gas in the balloon tends to stay in there. Now, the first thing we like to talk about is the velocity. And I might ask you if you could see the air. Take a demo. If you could actually see air and see the atoms of air, these atoms, bring my air atoms, would not just be sitting still. They'd be in rapid random motion, so everything's moving, and that's kinetic theory. So if you look at the air, you might look at an individual atom and say, well, how fast is that atom going? What's the velocity of an individual atom? And that's what RMS, we call it RMS, and I'll tell you why in a second. Velocity. And I like to say U RMS. The U actually is micron, okay? But if you think of that, someone is URMS, okay? RMS stands for root mean square, and then velocity is the micron. There's an equation for root mean square velocity now. The question I always asked someone was, well, how fast is a molecule going? You might think about that if you opened up a bottle of perfume and that perfume vaporizes into a gas, and you say to yourself, well, how long does it take perfume to reach my nose? And if you're thinking about the speed of the molecule just coming to your nose, if you're standing 10 feet away and it takes 2 minutes for the smell to get to you, you might assume it's going pretty slow. But in actuality, to bring this back, if you can imagine the number of molecules in a 22.4 liters, you'd have 6.02 times 10 to the 23rd atoms of gas. Well, if it's all moving, and if this is the individual perfume, say the green one or the red one, it doesn't move in a direct straight line, free right to your nose. It actually has to get through and bounce into other different molecules, and it ends up moving in a very random motion. So it doesn't get directly to you. It actually might end up going 2 feet forward, then 2 feet back, then 2 feet to the right, then 2 feet to the left. And so what you might think is a very slow-moving molecule is actually going very fast. It's just it has an enormous amount of collisions to go through to get to your nose. So here's our equation for URMS. URMS is, now I'm not going to really have this on a test, but I'm going to use it to derive Graham's law, is where I'm going with this. It's the square root of 3 RT over the molar mass. Okay, so that's my speed. The units are going to be in meters per second. So everything here has to be SI units. So if I start looking at SI units, the R you have to use is 8.314. That's the one with energy in it. And the energy in it is a joule, okay, per liter, per mole, per K. Okay, T is temperature, and that's again going to be in Kelvin, just like all gas laws. And molar mass, the thing that catches most people with molar mass, and you'll use this later if you go into AP physics, is that the unit for molar mass is SI. It's not going to be in grams. The SI unit for mass is going to be kilograms per mole. And that's where most people get stuck on this. Now a joule, as a unit of work equals force times distance. And the force is a Newton, and the distance is a meter. Okay, and F equals ma. I'll go through a little bit of physics. And that Newton is going to be a kilogram. Okay, and acceleration is meters per second squared. So a joule ends up equaling a kilogram per meter squared per second squared as an SI unit. And I'm just going to put that down to the side because I'm going to pay attention to the units in a minute. I'm actually going to take the liter out of this because the liter is taken care of in the meter squared part of that equation. All right, you have to use 8.314. That's generally the R, the ideal gas constant. Whenever you have energy involved, you're using 8.314. Okay, so let's find the speed. Find the URMS velocity of oxygen. So the thing I know about oxygen is I have to find its molar mass of O2. So normally we would say it's 32, 16 times 2, grams per mole, but I have to convert a gram to a kilogram. So I get 1,000 grams per 1 kilogram. So I got 32 divided by 1,000. So I get 0.032 kilograms per mole. And after that, it's all pretty easy. And I'm going to say at room temperature. So let's say it's at 25 degrees Celsius, which that's going to equal 298 K. Okay, so just plugging into this equation, the URMS velocity of O2 is equal to the square root of 3 times 0.08, 8.314. Okay. Now, if I look at all my units canceling out, everything's going to cancel out in there except for meters per second squared. So I'm just not going to really pay attention to units on this. Plug it in the temperature, it's 298 K. That K will cancel out with the 8.314, and that's divided by 0.032, and that's going to be kilograms per mole. The kilograms cancels out with the kilograms in the joules. Your moles comes out with your R. That's in the R. So what you end up with is meters squared per second squared as the leftover unit, and you're taking the square root of that. So 3 times 8.314 times 298 divided by 0.032. Then I'll take the square root of everything. And what I get is the RMS speed of a single oxygen molecule is 482 meters per second. Now let's look at that in miles per hour. So if I want to convert it to miles, there's 1,609 meters in 1 mile and 3,600 seconds in 1 hour. So 42 times 3,600 divided by 1,609. And I end up with the fact that oxygen goes 1,080 miles per hour. So as you walk through the room, that's how fast oxygen's hitting your forehead, 1,080, and so you wonder why it's not like a bullet through the forehead. Well, it has such a low mass. The mass is so light that that's pretty much what you feel as air pressure. Okay? It wouldn't damage you at room temperature, but if you encountered air that, say, was like 100 degrees Celsius, like the boiling point of water, it actually, at that point, it does cause cellular damage. So the faster it goes, the more it could possibly damage you. Now, let's try the hydrogen. Hydrogen is 2.02 grams per mole. So I'm going to convert grams to kilograms. So I'm going to divide 2.02 by 1,000. And the molar mass of hydrogen is 0.00202. Okay? And that's going to be kilograms per mole. So here I have oxygen, and here I have hydrogen. Plugging it into URMS, this is just a simple plug-in equation. So you get the square root of 3 times R, which is 8.314. I'm going to ignore the units right now. 298 K. K cancels out with my units. Divided by 0.00202. Kilogram cancels out with the kilograms in the 8.314. And then moles cancels out with the moles in there. And you're left with meters squared per second squared. So now this gas being so much lighter, it's going to be a lot faster. So you can see this equation. The molar mass is in the denominator. So as you become lighter, your speed goes up. It's inversely proportional to the square root. Okay? So times 3 times 8.314 times 298. So the URMS speed of hydrogen is equal to, now that's 108, we'll just call it, I'll round it off to 1900 meters per second. And if I put that through the same equation, make it miles per hour, divided by 1609 times 3600, just to put it in perspective, hydrogen would be coming at you at room temperature at 4,250 miles per hour, which is pretty crazy. Okay. Now, if I was to look at the ratio of hydrogen to oxygen, so compare the speed of the rate of effusion of hydrogen to oxygen, I would then say let's take the rate of hydrogen, divide it by the rate of oxygen, and that would be the velocity. So if I did it in meters, I have 1900 and 482, so it'd be 1900 meters per second divided by 482 meters per second. So 1900 divided by 482, and I got 3.94. So what I can say is that hydrogen diffuses at 3.94 times the rate of oxygen. Whenever you have the faster molecule on top here, you're going to be greater than 1 for your rate. If you flip this and put oxygen on top, the inverse of that would be 0.253 or 0.254. So you could say oxygen diffuses at 0.254 times the rate of hydrogen. And whenever this is below 1, that means your slower gas is on top and you're comparing it to your faster gas. I'll mention that later when we do Graham's law type problems. Okay, if I did this in miles per hour, 4250 miles per hour over 1080. I don't think that looks quite right. I guess it is 3.94. So whether your rates are in meters per hour or miles per hour, meters per second rather, they still have the same ratio. Okay, and that's what I just wanted to show you, that the ratio would remain the same. Now, Graham's law of effusion. What Graham's law does in words is it compares. Now, Graham's law of effusion is section 10.8. This is still 10.8. Okay, and here's how you would derive Graham's law of effusion. If I took the URMS speed of gas number 1 and divided it by the URMS speed of gas number 2, that would be 3 RT over the molar mass of 1 divided by 3 RT divided by the molar mass of 2. Okay, R and T, this would be at one temperature. So assuming that my temperature is constant, 3, R, and T will all cancel out. I would be left with 1 over the inverse over the square root of molar mass 1 over the inverse of molar mass 2. Now if you're going to divide fractions, you invert and multiply. So here's Graham's law of effusion. Rate of number 1 compared to the rate of number 2 would equal, it's the inverse of these, so the molar mass 2 ends up on top and molar mass 1 ends up on bottom. And because you're dividing by molar masses, you no longer have to worry about using SI. You don't have to convert it from grams to kilograms. You can just plug in your molar masses. So let's compare this to the work that I just did. Using this, compare the rate of effusion of hydrogen to oxygen. Okay. I would say the rate of hydrogen compared to the rate of oxygen is the inverse of their molar masses. Now oxygen is 32.0 grams per mole. Hydrogen is 2.02 grams per mole. Units cancel out. 32 divided by 2 is 16. Close to 16. 32 divided by 2.02. Take the square root. And the answer here comes out to be 3.98. Now I would say the only difference would be the sig figs I used here. Just checking, but pretty much getting the same ratio, and that's Graham's law. So we can use Graham's law to do types of problems where we find their molar masses. All right, I'll give you a few examples of those, and I'm going to shut this off now.